We present Avoid Everything, model-free, collision avoidance with expert-guided fine-tuning. Avoid Everything is a novel, end-to-end system for generating collision-free motion toward a target, even targets close to obstacles. It consists of two components. 1. Motion Policy Transformer, a transformer architecture for end-to-end joint space control from point clouds, trained on over 1 million expert trajectories, and 2. A fine-tuning procedure we call Refining on Optimized Policy Experts, or ROPE, which uses optimization to provide demonstrations of safe behavior in challenging states. Our model, Motion Policy Transformer, expects a calibrated point cloud of the scene. We then mask out the points on the robot and replace them with points sampled deterministically from the robot's mesh, and add in points sampled from a mesh of the robot's gripper placed at the target pose. This point cloud is then passed into a point net with 3 set aggregation layers. Then, the output point cloud features are passed through an 8-layer transformer along with an embedding of the joint angles and a learned constant embedding. Finally, the output token corresponding to the learned constant input is then decoded into a delta joint configuration. We trained Motion Policy Transformer separately on 2 classes of simulated environments constructed from primitives: 1. Randomly constructed 2x2 cubbies, and 2. Randomly constructed tabletops with a collection of objects on top. The planning problems in these environments are chosen randomly, and the solutions are planned using AIT star, along with spline-based shortcutting. For training, we used 1.25 million cubby demonstrations and 2 million tabletop demonstrations. ROPE is a fine-tuning procedure that we use to further improve collision avoidance. When fine-tuning with ROPE, we begin with the pre-trained model. We iterate through the training dataset, in which each data point consists of a scene model, a state, a reaching target, and the next state. For each data point, we roll out the policy starting from the state until it either collides, reaches the target, or times out. If it collides, we create a new data point, where the state is the rollout step preceding the collision, and the next state is produced by using optimization to correct the colliding rollout step. If the rollout does not collide, we hold on to the original data point used to start the rollout. We maintain a ratio of modified data points to unmodified ones. When we have amassed enough of each to form a batch, we compute the training losses and perform a gradient update. We used simulated depth images to compare our performance against classical methods with common perception pipelines, as well as with motion policy networks, the state-of-the-art method for learned end-to-end collision-free motion. We found Avoid Everything collides significantly less often than these techniques. Here, Avoid Everything safely avoids a moving obstacle, despite only observing the scene from a single depth camera. Avoid Everything can fail around obstacles that fall far outside of the training distribution. This chair is out of distribution and has thin legs that the system struggles to avoid. Despite these challenges, Avoid Everything can navigate cluttered settings and avoid fast-moving objects due to our novel network architecture and our hard negative fine-tuning procedure.